Thank you. I'm Chris Harrelson. You probably heard a little bit from me if you were at BlinkOn 3. I am the tech lead for the Paint team. Just like the layout team that Emil referred to yesterday, Paint team is another one of these teams we've formed, which is actually across multiple offices, as all of the teams are, and also between Google and non-Google contributors. In particular, there's one or two Opera people who are contributing to Paint. To be a long-term owner of code and think about all of the challenges there. So Slimming Paint is actually the project that we're doing right now. Okay. That's weird. Okay. The computer got sad. Slimming Paint is basically the only thing we're doing right now, though we are doing some planning for other things in the future. So Slimming Paint actually has, it's a large project. It's about 10 full-time contributors across Blink and the Compositor. And we also have several part-time contributors in the Compositor and doing support work in terms of performance and API adjustments and things from Skia. So it's really an amazing cross-team project that is actually, I would say, minority Blink and majority other people. So this is great. And this is, of course, the first major project that we've done since the Paint team was officially founded in January of this year. So what is Slimming Paint? Slimming Paint sounds like you're losing some weight, but really it's compositing after painting rather than before. So maybe it should have been called the CAP project. By analogy with repaint after layout. So why would you want to composite after paint? I don't know, but maybe we should just do it anyway. And maybe we'll learn through this talk why. So what does it mean to composite after paint? Let's compare the old system with the Slimming Paint system. Before, we were compositing subtrees of layout objects. Not exactly subtrees, but let's just say subtrees. Where you say like, oh, like all the things below this thing with a wheel change or a 3D transform should go into a composited layer because that will be convenient for caching and performance will be improved. And the second thing is how invalidation works. Paint invalidation means writing down which of the pixels on which of the composited layers on the screen need to be redrawn. And that is done with by computing rectangles that contain the areas which need to be redrawn. And so what the code actually does is when you change the style on a layout object or other layout objects, it figures out which of the layout objects have a cascading invalidation that needs to happen. It computes the bounding rect of all those things. It maps it to the space of the composited graphics layer that contains those layout objects and then tells the compositor about that. So after Slimming Paint, we are going to composite based on what I call display list chunks. So that the painting phase of Blink outputs a display list. It actually sort of already does this today. It's just that the display list is an opaque, immutable thing. I'll get into this more later. And so we're going to have a display list that you can be able to break up into little chunks and then stick some of those chunks as appropriate into composited layers. And so rather than deciding on layout object subtrees, you decide on display list chunks. And the second thing is that the invalidation will change. To be based on layout objects, not rectangles. So if you invalidate just the background of a particular object, then that is the only thing that's invalid, not any things which happen to be in the subtree below that layout object. And there's technical reasons why this is the case, which I hope will be illustrated with some examples. So here's an example where we have two divs, one of which has ID A and one of which has ID B. As you can see from the red text, the one with ID A has a will change transform, meaning that the developer has given a hint that you should probably composite this thing because in the future I intend to mess with its transform and it would be more efficient if you just do so. And for div B, the developer says, please just draw it at its appropriate position. So pre-Slimming Paint, let's go through the way that things would work. So the two divs will be drawn on the screen, separately. One of them has some text in it saying composited content, another says div, so you can distinguish them in the example. So how do the layers get set up? Blink will decide that div A gets a composited layer because you set will change transform on it, and that is the blue rectangle in this screen. So that will get a different composited layer with its own backing texture that is independent of the other one, so that if you draw one or the other, you don't have to re-raster the other one. And the second div is painted into the red layer. The red layer is the root graphics layer, which is always present on every web page, and which is draws everything unless you indicate otherwise. So if this is an interesting example, because you're sort of actually painting into a graphics, into a layer which is sort of a parent of the blue one. So just keep that in mind for later thought. How does invalidation work? So let's suppose we change the text composited to be uppercase. What will actually happen is that the layout code will notice that change to uppercase, and so the run of text, there's actually sort of like an object below layout object which contains the run of text, and we compute its bounds and we say, okay, that's an invalidation rect, and maybe we're clever enough to do that, and so we send that we send that rect, the dark green rect, to the compositor to say you need to redraw this run of text. The compositor will actually expand that to the bounds of what it calls a recording tile, which is like the units of paint that the compositor is willing to do. It does things in units so that it can be more efficient. And it will ask Blink to paint all the things in the light green rectangle within the containing blue composited graphics layer. And then when raster occurs, raster is the second phase of what the compositor does. First, it asks Blink to paint. That draws into a display list, even today. Display list is called skpicture. And then later on, when it gets around to it, the compositor will raster things into pixels. And it rasters the exact same sized tile rect that it recorded in the first place into an skpicture. So what happens with slimming paint? So we have the same example. I posted it above for reference. And what we do is we output a display list. So let's look at what the display list has in it. So here we have we have the background, the border, and the text for div A and div B, which is what you would expect to be the sequence of low-level paint commands. But we have these two special things that are in there: the will change begin and the will change end. And what those are placeholder hints that tell the compositor or whoever wants to draw this content that, by the way, the thing between this begin and end is something that you probably want to cache in a composited layer. It may or may not be required depending on the type of hint, but it's a hint that this is a good strategy. So this will be used later on, of course. So in layerization, so what Blink will do is it will send essentially the entire display list over to the compositor. The compositor will walk through that display list in a cartoon sense. I mean, we have optimizations, which I'll talk about later, but it walks through the display list looking for these hint boundaries. And the boundaries of where like a will change begin and a will change end happened are the chunk boundaries that I referred to earlier. So it divides things up into these chunks. It walks through the chunks. For each of the ones that sort of require compositing, like will change probably requires compositing, it goes ahead and just sticks that in a composited layer. And then if later on it discovers things that might overlap the previous composited layers, it promotes them as well in order to preserve correctly painted output. So how does invalidation work? Like I said, we do layout object-based invalidation. So in this case, the span that contains the text that was capitalized in the example is the only thing that's invalidated. And so ideally, that's the only thing we need to paint. So how does this actually work? How are you painting part of the thing? I don't know, somehow it does it. We'll talk about that later on in the talk. But conceptually, it paints only the things which actually were invalidated, not their subtrees, and perhaps not even their paint phases, which were, if you're clever enough, were not invalidated. And then it somehow splices that into the existing paint list, and then tells all that to the compositor in terms of a diff. So you say like, here, compositor, here's my new display list. And by the way, only this little span display item within your complete display list is the thing that changed. The compositor will map that to its composited layer decisions. Because remember, in this architecture, Blink does not actually know what things are composited. All it knows is like what the hints were and what it recommended to the compositor, but it doesn't actually know what decisions the compositor made, and this is an important thing. So the compositor will say, oh, I actually, all those blue things are in a single composited layer because I tossed them into such a thing based on the will change. And And this span, because of some geometric metadata we have, is easy to map into the space of the blue composited layer. And so therefore, the compositor will be able to figure out the exact bounds which need to be re-rastered within that composited layer. And so once it has those bounds, it just goes ahead and re-rasters the containing tile using the display list. Okay? So that's a cartoon of how things work. So let's go through another example. So this is a non-deprecated paint layer example. Deprecated paint layer is the artist formerly known as render layer. And it's a concept within the layout tree in Blink that's used to represent stacking contexts, and it's also used to represent the boundaries of the potential Blink layerization decision. So when I said like these display item chunks that the compositor uses to decide when to make layerization breaks, the equivalent in the existing system is the render layer, or the deprecated paint layer in the current code. So in my previous example, I was careful to have both of those divs be stacking contexts, which means that they're positioned and had a z-index according to the web specification. So if you remove those things, what happens? If you draw them, they actually look the same because they don't overlap each other. So what happens if you overlap them? You take div B and you set a negative top margin on it, which even though it's not a positioned element, will push the element north. And you see that if you try this in Chrome today, div B will render underneath div A, because you notice that div A has a will change transform, which requires us to composite it. But because div B is not a render layer, it can't actually draw it on top. And so Chrome renders this incorrectly today. And so because as you can see, div A in paint order, because it's later in DOM order, you're supposed to draw it on top, but in fact, Chrome renders it not on top today. And this is what's called the fundamental compositing bug. And it's a fundamental flaw in the way that we do our compositing decisions today, which is actually not fixable in the system. And I'll note that Safari has the same bug. Firefox, and I assume IE does not, because Firefox actually has, I should mention, or Mozilla Firefox Gecko has already implemented something very similar to Slimming Paint, where they actually do display list generation and then layerization on the display list rather than layout object subtrees. Okay, so with Slimming Paint, everything will be great somehow, because the display list that will be output will look something like this. And then the chunks will be able to be grouped because the compositor is able to take arbitrary chunks and promote them. It doesn't care if the chunk happens to come from a render layer or not. And we win, and we can paint this correctly. One other thing to notice here is that, excuse me, is that the green, which represents the content from div B, is actually interleaved with the display items from div A. And this is because when you don't have stacking contexts on web pages, the painting order is actually interleaved between the elements when you draw multiple things within a block level context. So let me just give you a small hint of all the fun that results from that, or that results in that. So this is a famous web page among web painting people, which explains the order in which you should paint things that are not stacking contexts. So you say like, oh, is it a root element? If so, do the color and image. Is there some block stuff? Then do the background, but don't do the foreground yet. And then do the floats, and then do the position negative z index, and then do this other thing, and do this other thing. And at the very end, paint your outlines. So it's not true that painting is a strictly contained thing, as you would intuitively think from the hierarchical structure of a DOM. It actually, there's interleaving going on, unless you have stacking contexts. If you set a stacking context on everything, then you win. But that actually makes it difficult to draw various kinds of output that web developers want. So they don't actually do that. Okay, keep that in mind. Here's another example, which is exciting and difficult, and Ian Volokh knows all about. which is scrolling. Suppose you have an overflow scroll element, which let's say is a stacking context because that makes things easy, and you're on a high definition screen. This means that you actually have an opportunity to automatically make composited layers for that. Let me check the time real quick, 10:15. Okay. You have an opportunity to automatically make the contents of that scrolling thing its own composited layer, so that when you scroll it, you don't actually have to re-raster anything. You just sort of take a texture and you move it up and down in the scene, and everything is super fast and you win. So we have implemented this in Chrome. For technical reasons, which I won't go into right now, it only works on high definition screen, high DPI screens, which means a Retina MacBook, certain Chromebooks, and Android. So Android is by far the most important customer of this feature. And so here, the compositor, the Blink will actually notice that it's overflow scroll and other various conditions hold. And so yes, we're going to go ahead and make a blue composited layer here that contains A and B. So this is the slimming paint example version of this, where you just, it's pretty straightforward to just take those two things. I did not actually, in this example, draw the begin scroll display item and the end scroll display item, which is the compositing hint equivalent of will change, but that will be present as well. So what happens if you don't do stacking without it being a stacking context? In this case, the web painting algorithm makes things even crazier, because setting overflow scroll does not require something to be a stacking context. This means that content that does not scroll can, in bizarre ways, insert itself into the paint order of scroll, which completely wreaks havoc with attempts to make composited layers, because you can't just like take A and B and put them into a composited thing and then draw C separately, because C actually draws in between A and B, because in this example it has a Z index between the two. And there's even more excitement to do with all the strange ways that this interacts with the controls, the scroll controls that go on the side of your overflow scroll, and just complete havoc results. Here's another exciting example, fixed position. On Retina and other high DPI screens like Android, like I said, we also composite fixed position elements. And this is really important because with fixed position, you scroll the web page, but the fixed position thing just sits there attached to the viewport. And so it's totally natural for that thing to be its own composited layer, and you can see why that's actually necessary in order to avoid rastering the entire screen essentially on every frame. And so all the excitement of non-stacking contexts and details of fixed position make this actually very difficult to implement with the current layerization system in Blink, basically for reasons similar to the examples I gave before. So let me give a little bit more data about how complex we have had to implement the code that does compositing in Blink in order to even achieve the things that we can achieve today. Yet we still have bugs due to the fundamental compositing bug. For example, there have been 2 bugs in the last 2 weeks due to like obscure situations with scrolling, which we screwed up. So as Kentaro Hara mentioned yesterday, Blink doesn't have very many comments, and people tend not to write comments. But this code is so complex that not only did we write a comment, we wrote an essay explaining all the bizarre ways in which you can make these graphics layers combine together in order to implement all the stupid, ridiculous, but yet important corner cases of the web. So here you have, like, there's an ancestor clipping layer, and maybe there's the main one, and then maybe there's a child transform one, which maybe has a child containment one below it, but maybe it won't. Maybe instead it'll have a scrolling container one, and then maybe it'll have a block selection thing, and who knows what that means. And every single time those of us who are supposedly experts in this code come into it, we have to read this essay again, and then like jump up and down and like have some coffee and think about it, and tech up yet again on the code which we forgot because it's so complex you forget it in a week. So this is the first page of the comment, but actually the comment keeps going, and then it keeps going some more, and then it's like, oh, but also we have squashing. What is squashing? Squashing is like some other crazy thing that we use to compensate for performance problems in the rest of the compositing system. And I'm responsible for squashing, but on the plus side, it finally like beat into my head that we really need to do slimming paint. So I'm kind of happy I did squashing. Okay, so that's the end of the comment. That's exciting. It was only a 4-page comment. And it's also exciting that the compositing code has more comments per line of code than the rest of Blink. So that's exciting. Okay, so why should we do slimming paint? Let's recap 2 reasons we found so far. One is that Blink paints things wrong. That sucks because that's not correct. And it actually does cause problems. There are real web pages which have to work around this craziness. It also means that Firefox and Chrome and IE are not compatible in this respect. And so people have to actually test and build their websites slightly differently in order to work on all the browsers and all the... so it's bad for all the reasons you usually think. I hope I've justified that there's an uncomfortably exciting amount of complexity in Blink due to this. Yeah, that's an understatement. So here's some more reasons why you would want to do layerization, composite layerization after paint. One is GPU rasterization. What is GPU rasterization? This means instead of like walking through a display list using code on the CPU to draw it into pixels, you do that with shaders in the GPU. So this in the code word of this project in Skia is called Ganesh, and it actually is implemented. We launched it last year on Android, and I would say perhaps it was the single biggest improvement to performance of the entire year for Chrome on Android. And the reason is because GPU rasterization in almost every case is way faster than software rasterization. And in fact, the reason we do, so now let's tie this back to compositing. The reason we do compositing is for caching. The reason we need to do the caching is because the rasterization system is not fast enough. So if the rasterization system is all of a sudden super fast, why are we even compositing things at all? Why do we have this crazy complexity? Why are we like wasting time doing these crazy algorithms? Why don't we just get rid of all this stuff? So, so we actually at one point considered like maybe we should just fork the whole things and make a fast path for GPU rasterization. But actually the nirvana in GPU rasterization is not actually fully achievable in all cases. And furthermore, there's a huge variation in platforms. So we're going to do so this motivates slimming paint because if the compositor decides what to do about a will change transform, the compositor is fully welcome to say like, no, I'm just not going to composite that because I don't feel like it because I think Ganesh is going to do it faster. And that will be easy to implement by just saying like, no, please don't do it because the hardware platform happens to have the following characteristics. If you were to try to implement that in Blink, it would essentially be a pipeline layering violation, which is bad for lots of reasons. Second thing is that there are a lot of features that Chrome has that are now compositor accelerated. For example, we can run various web animations on scroll, transform, and opacity directly in the compositor without involving Blink, which has all the parallelization benefits you would think. And those animations like can do things, right? They can move things around. And Blink doesn't really know what those things are doing because it doesn't understand them very well. And so Blink has to be conservative about what it might do. And it's say like, oh, well, if you're going to maybe animate this thing over or down on top of this other div, then I should probably just promote that div to a composited layer just in case. When in fact, maybe it didn't actually need to do that. Same thing goes with scrolling. There are like corner cases in scrolling where you have to be conservative about things because stacking context, non-stacking context painting is crazy. And there are a couple of feature-looking reasons why you would also want to do slimming paint. One is you can imagine doing like a hyper-fast platform where like you just want to change the background on an element on every frame, and so you tweak the display item corresponding to the background, and then nothing else happens in principle, and then you just raster the thing and it's super fast. Second thing is that this is kind of subtle, but the output of the paint as designed with slimming paint is actually independent of Blink, yet it retains semantics. And by retaining semantics, I mean like these layerization hints and other things are like in there, so you can actually manipulate this thing independently of Blink, which is good for some componentization and and perhaps Compositor worker and other use cases. Okay, so now let me get to some implementation highlights of Slimming Paint and why it is that it takes all 10 of us to do it and still takes a year to accomplish. So, like I said, one thing we do is we invalidate individual layout objects. Another thing is that we generate display lists and somehow mutate pieces of them and merge those pieces back in on every frame. How does all that magic work? Third thing is, what about all these auxiliary data structures? If you've worked at all with the Compositor integration with Blink, you know that there are various pieces of metadata that we stick on graphics layers to say stuff like, oh, by the way, the web page has a wheel event handler on this scrollable graphics layer, and so you probably shouldn't be doing composited scrolling because it needs to run JavaScript. Or you have touch events in this part of it, and likewise, if you tap on that part of it, you should pay attention to those events before continuing. Or like, this is how web animations are plumbed. You attach metadata on there that says like, this thing has the following animations on it that will occur, all the stuff in order to run the animation. Second thing is that, like, how do you even implement the layerization algorithm in the compositors? Like, how complex is it? What are the challenges there? And the last is like, how do you actually raster this display list thing as quickly as we can raster the existing system? Okay, invalidation. It turns out that the invalidation system is already at its lowest level at the layout object level. When you change the style or whatever of a layout object, what we actually do is we set a bit that says like, this thing really should be invalid. You should go ahead and re-raster it. And then pre-slimming paint, we have some code that walks through the layout tree, computes the bounding rectangles of all the things which said they needed to be redrawn, and then unions all that stuff or adds them up, and then sends them over to the compositor. So that last step, of course, is no longer needed with Slimming Paint, because all we need to know is which layout objects changed. but the current implementation of Blink cheats. It doesn't really cheat, but it cheats from the point of view of Slimming Paint, where, like, suppose you invalidate a control, a certain like CSS property on a checkbox control, which has underneath it a shadow DOM that implements stuff based on that style. Until like last week, we invalidated only the control, but not the shadow DOM. And because the control contains the shadow DOM in its bounding rectangle, the previous system was correct, because the rectangle hid the subtree. And so instead, with Slimming Paint, we can't do that. We have to invalidate the whole subtree. So in some cases, there may or may not be like small performance hits because you have to invalidate those things. But most importantly, we need to find all of them and fix them. And there are all sorts of like weird corner cases, and it's difficult to like sift through the hundreds of thousands of lines of code. So we've implemented a bunch of clever stuff to put Slimming Paint into a mode where we're trying our hardest to assert and find these we call them under invalidations, and then once we found them, we fix them, and the world is a better place. So painting, how does painting work? So what we do is at the moment we walk the entire layout tree on every single frame, regardless of anything, and for the layout objects which were marked as needing invalidation, we, of course, when we need to add the display items for them at different phases of the paint algorithm, we just regenerate them and stick them into the list that we're building as we go. For things which were not invalidated, we don't want to do that work because there's no need to. But we still need to traverse through those layout objects in order to preserve the correct paint order of the screen. Because of that web page I showed you, in which the web painting algorithm is super complicated, and you really don't want to try to be clever about making it faster. Or at least it's difficult to do so. Aha, thank you. For ones which are not invalidated, we still visit them, but what we do is we detect that they're not invalid, which is easy because there's just a bit. And then when you would have otherwise generated a display item, we instead generate a caching display item, which has the same ID so that you can look it up later, but it doesn't have anything else. And then you exit. So at the end, what you have is like a partial display list, which is of basically the same length as the previous frame, except that a bunch of things are caching things. And then you walk through it, and you replace all the cache things with the real things by just copying them across. And you have to optimize it some in order to like reduce the number of hash map lookups and memory size and take advantage of certain common patterns, but that's basically what it does today. And we have ways to optimize that in the future, which I won't get into right now, in order to avoid walking the entire layout tree, and basically to avoid walking the entire layout tree and having to walk the entire display list, because that's an O of n, which violates the principle of like only change what you need to. So let me give you a little bit more information about how the display list is represented. We have different types of display items. The basic commands that you would expect to see in a display list, like draw a little bit of text, or draw a line here, or draw a shadow here, or something. All those things are contained in a drawing display item. A drawing display item is simply a wrapper for an SK picture. An SK picture actually contains the meat. So that's that. And then in places where you want to clip an entire subtree, like you have an overflow hidden or whatever on an element, you put a begin clip and an end clip that bracket the rest of the things, so that the system that rasters knows that it needs to clip that stuff. Same thing with transform, fixed position, and so on. And so we've designed these things so that they're basically wrappers around what we were already doing in order to generate an SK picture Skia object. And what this means is that the existing paint code can actually be used basically as is, but with some annotations on top to basically say like, okay, you're inside of this layout object, and you're going to paint its background. Make a drawing display item, and then like listen to what all the things you did during drawing that background, and then when it's done, wrap that up into a thing and stick it in the display list. So this means that we don't have to rewrite the paint system. We just need to annotate it with these things, which is cool. Merge, we already talked about that. So there are various auxiliary data structures, which I referred to earlier, for composite-driven animations, input events. There's also some data structures that we're going to have to compute, which are necessary in order to make the whole system efficient. So right now, the compositor actually spends quite a lot of time computing things like the visible content rect for a graphics layer. And visible content rect means like if you take a graphics layer and you project it into screen space, how much of it is actually visible to the user, and how close is it to the screen. And based on those things, we decide whether or not it's so far away that it's not rasterable or should be pre-painted or all these things. And we also use the visible content recs to do compositor hit testing. So when you tap on the screen, the compositor gets the first crack at listening to it, and it uses these recs in order to determine the mapping between a pixel that you tapped and which graphics layer it corresponds to. And then if the graphics layer is scrollable, then you start a gesture for scroll. Or if there's a touch event listener, then you don't do that because the main thread needs to get it, and so on and so forth. So there are all sorts of and there are other use cases like how do you like pre-decode images and pipeline those things, and you need clipping and raster culling, geometric data structures and stuff. So a lot of these optimization use cases are going to be handled by something called property trees. What are property trees? Property trees are, you can think of them as like subsets of the geometric things that you would want to do on a web page. So the transform tree, for example, you can think of it as a sparse representation of like the DOM sort of that has one node for every element with a transform with a 3D transform on it. And that makes sense because like if you have a web page scene, then everything is composed of like these 2D surfaces that are separated by these 3D transforms. And you can imagine how that's super useful for computing visible content recs. And the reason why it's efficient is because in typical use, there are many fewer transform 3Ds on a page than there are elements on the page. And this means that this tree is super sparse. In fact, it's a lot more sparse in many cases than the number of graphics layers you need in order to draw the scene. For example, Ian gave me an example let's just say it's accurate, where I'm sure it's basically accurate, where I think on the verge, you said? On the verge, there's something like, I don't know, let's say 60 graphics layers, but only 6 transform nodes. Because a lot of those graphics layers are those like crazy things that do all sorts of stuff that are not really important to computing visible content recs. So that's cool. There was also clipping trees because composite layers can clip each other, and that's really important, obviously, in order to draw correct things to the screen. Scrolling is sort of a special case of transform, and opacity and filter because the compositor needs to do various kinds of blending and filtering between composited stuff in order to draw things correctly. So how do you implement property trees? Property trees, you can imagine, can just be computed from layout, actually. They can also be computed from the display list because the display list is very careful to output those like begin transform, end transform, begin scroll, begin clip, begin filter. So you can just like walk along it, and whenever you see it, like, oh, that's a transform node. Okay, I'll stick that in my transform tree. And that's actually likely to be what we implement for some paint. You can also compute the property trees directly from the CC layers. CC layer is like the compositor representation of a graphics layer, if you know the Blink terminology. And I'll talk about this in a second because it's important for the way we're staging our work. I have until 45 after. Okay, I'll speed up so we have time for questions. So compositor layerization splits things into chunks and then walks through the thing and promotes the things that have to be promoted, and things that you really don't want to promote but overlap things which you promoted, you also have to promote. And so you need some data structures there. And you can implement the equivalent of squashing very easily with this because you don't have to worry about semantics of the web painting algorithm. Okay, so let me quickly give an overview of phase 1 and phase 2. So Slimming Paint, I hope I've explained some of the reasons why it's a very difficult and long-running project. So we want to split it into 2 launch phases. So we can launch some of the things and make sure that their performance and correctness is good enough, and then finish the other things. So in our phase 1, the red things will change, the black ones will not. So we're going to retain the existing way that we create graphics layers in Blink. And instead, we're going to focus on invalidating based on layout objects, making that exactly correct, computing partial display lists, and the merge algorithm that I described earlier. And then at the end of all that, we're actually going to take the display item list and convert it back to an SK picture in order to raster that. And the reason we convert it to an SK picture is because SK picture already contains within itself lots of optimizations to make the rasterization faster, which is going to be convenient for phase 1 so that we don't have to think about it just yet. In phase 1 on the compositor side, we're implementing, we've abstracted a recording source and a raster source concept so that we can implement a display list version of what the compositor does for recording and for raster, and separate that from the non-display list version and implement the various helper routines and stuff. And again, we're actually going to raster from the SK picture, not the display list, even though it's represented in the compositor for the reasons I just gave. And also, essentially, in phase 1, we are going to convert this thing called calc_draw props in the compositor to use property trees. And calc_draw props is the thing that previously was computing the visible content recs, the clipping, and all the other properties that you need in order to do all the things the compositor does. And so we're going to convert that over to property trees by computing property trees from the CC layers. So basically, you can think of like all the users of these data of the like visible content recs and things in the compositor will be able to use the property trees, but for the moment, we won't be computing the property trees in Blink where we should be computing them. So in phase 2, we're going to do everything, which means like Blink will now be in charge of painting. It will execute paint synchronously after layout and validation is done. We're going to completely change the Blink to CC API to send display lists rather than graphics layers. We're going to delete the compositing code in Blink. Yay. And all these metadata and property trees and whatever we're going to add on to the side of the display list. In CC, we're going to stop having the concept of a main thread CC layer. The commit from the main thread to the compositor thread is just going to be the display list and the other metadata. And the layerization algorithm will be executed on the compositor thread, not on Blink, which we hope will also be another thing that improves performance. And does some plumbing and then some art trees or something. So phase 1 is nearing completion. Property trees are done. We may or may not be able to launch them with M44, if not M45. And the rest of Slimming Paint phase 1 we expect to be able to launch with M45. The implementation is complete. It's just that we don't have all of the bugs ironed out yet. We still have more under invalidation and correct and some other flavors of bug that we just need to drill down and get all the layout tests to pass and then ship the thing. We also have a small number of performance regressions due to the overhead of display lists. But due to some diligent and clever work, we've been able to get that down to something in the neighborhood of a 10% regression on full page re-record of large pages in our regression test set, which we think is probably good enough to launch, given that we should be already a win on partial page updates. And phase 2 is starting now, especially in the compositor side. We're going to be checking in the new API and starting to implement the layerization algorithm. And we hope to launch that in Q3 if all goes well. So that wraps up my talk. Maybe you have questions. But first, should I show you a demo? OK. So let's turn on Slimming Paint. Oh, wait a minute. It's already on. There's my demo. I presented this to you in Slimming Paint. Any questions? Yes, Justin.
So I was wondering if the layerization decisions could be based on some performance heuristics that determine whether a chunk should be rendered on the GPU versus the CPU.
Yeah, sure. Why not?
Okay. Is it in the plans?
I mean, all these sort of like conditional layerization things are in the like post phase 2 plans of like, let's just, now that we have the thing, let's take advantage of it. Let's implement faster paths in Blink that are done cleanly. Let's implement conditional layerization. Let's experiment with turning off compositization for fast GPU raster mobile devices. That's another thing that we want to do. We meaning Chrome wants to do. So it's all very exciting. It's a brave new world. Question from Christian.
So it's great that this is fixing all the bugs and is helping with the complexity, but I was just curious, do you have any performance numbers so far?
Yes, we have lots of performance numbers. We do a lot of regression testing on top sites, and also we have a cluster telemetry continuous. We run the cluster telemetry basically every day on the top 10,000 sites. And so in our benchmarking of paint and raster, the raster time is identical. The paint time is between a 10 and 15% regression on average for a full page. But if you do a partial page update, it's actually faster. And memory is, Jeremy, what's the memory number? OK. So we're not measuring everything, but memory is within 50% or something like that, I think.
Thanks.
Yeah. And with respect to the concerns about overall Chrome memory, we're pretty sure that the display list and the associated data structures is not nearly as big a component of overall memory as like texture size and V8 heap and stuff. So we're not as concerned about a 50% regression there.
So further to that, are you also planning on collecting performance data with UMA from the field? So in case our
yes, we've implemented time and memory UMA statistics where we've done our best to make a metric which is apples to apples pre-Slimming Paint to post-Slimming Paint, so that we can guess whether or not we're making users' lives worse.
Awesome. And should we be launching with a finished trial, or do you think we can just flip it on in 45?
I'd prefer to just launch it, yeah.
I guess we can always, if we launch it and...
Exactly. It's a flag. Flags can be turned off.
Yep.
It allows you to do a what?
User holdback.
Yeah, you can do holdback experiments. That's true. Ian.
But one other thing on the memory front. Since we were doing squashing before, and squashing was complicated, we couldn't put together layers that we would like to put together. So we should be able to squash a lot better and have, fewer textures. So kind of optimistic about us, having nicer layers and eating less memory in that front.
Yes, because there is overhead to do with the number of layers you have. And so, yeah, agreed. Okay, thank you.
All right, everyone, we'll go into a break now. But don't forget, later this afternoon, there is going to be a Q&A session. So there is a Google Moderator link on the one-pager. Please click that link and put down any questions you might like to ask a panel this afternoon. Thanks, everyone.
Thank you.